In this session, we'll be looking at how ions move through solutions and how this affects their ability to transport charge through that solution. So when we think about ion transport, there's a number of factors which affect their ability to move through the solution. Ions move through an electric field, and any electric field has magnitude and direction. All of these exert a coulombic force on our ion. But as it's moving through the solution, it experiences resistance, it experiences movement against opposite ions, and it experiences solvent drag. We covered this in terms of an ionic atmosphere and solvation shells. And these are the models that we've explored already. Without the electric field, however, ions will not migrate. They won't move through solution. And while it seems like we're stating the obvious, it is important to remember that the electric field is absolutely vital for electrochemistry. So understanding how it works, how it behaves, is a necessary component of our study. The electric field itself is measured in volts per meter, so a potential difference over a distance. So if we think about what's going on between two uniform plates, the electric field, we assume, is uniform between these plate electrodes. By convention, it travels from positive to negative. So our field goes from the positive electrode to the negative electrode. That's simply a convention. This field exerts a force on the ions in solution, which we can fairly easily quantify, where the force is the charge number of the ion multiplied by the charge on the electron and the electric field itself. This is the force which is driving our migration forward. It's the thing that's pushing our ions through the solution. Now, one thing I'd like you to make sure you're happy with is that the units are indeed congruent here. So make sure you understand the units of force, the units of charge, and the units of electric field, and make sure that you understand that these units are indeed congruent. The shape of the electrode is also important in defining the electric field. So if we think about paddle electrodes, so those plate electrodes we've been kind of looking at, if we look at them from above, we imagine them as two plates, our positive and negative. But if we think about rod electrodes sticking in to the solution, they would have a circular cross-section. Between these two diagrams, we're going to have a fixed potential difference. And as we explore this, we're looking at the electric field between them. So, quick convention, a longer field line represents a weaker field. We justify this as the electric field along a field line is equal to the change in voltage across that line divided by the length of it. Or if we're looking in solution, we look at the potential, this delta phi, divided by the length over which it acts. Okay, so these are the kind of things that we're looking at with our electric field. If we imagine the electric field in our plate electrodes, the electric field has straight lines between the plates, so there's a uniform field between these plates, but outside we start to get curving of these field lines. So we get this variable field, longer line, weaker field, because of this field equation that we have here. If we think of rod electrodes, however, they're not uniform anymore. Those lines curve through the solution, which means no matter how we act with a rod electrode, we have a variable field. So this is imagining the shape of the electric field and understanding how these things will potentially behave. We now want to think about the drag forces on our ions. Now remember, the drag forces impede that ionic flow. In this case, the diagram's representing the effect of solvation shells as well as the ionic atmosphere. It's affected by a number of factors. So we've got the things attached to the ion, but we also need to think about the solvent viscosity. This carries the symbol eta here. We think of the radius of the migrating species, whether that's the radius of the ion plus the solvation shell. This is all summed up in a term called the hydrodynamic radius. It includes the solvation shells and it includes any averaging effects that goes on there. There's also the speed of motion. The faster an ion moves, the more drag you would expect it to experience. And all of these factors are summed up in Stokes' law, which relates the force on our ion to the viscosity of the solvent and the hydrodynamic radius. We'll come back to this later on. It's important to recognise that the drag force on our ion is a combination of all of these factors together. Okay, so let's think about the drift speed of our ions. What is the maximum speed that our ions travel? So this is the constant speed reached when all the force is balanced. So when the electrical force pushing the ion through solution balances the drag force. Well, we've got our definitions. We've defined the drag force, we've defined the electrical force, and all we need to do is just simply equate them. This allows us to find the ionic drift speed S as a function of our electric field, solvent factor, and the hydrodynamic radius. Another way of looking at this is to consider ionic mobility. So if we define another term, ionic mobility of U, this is simply a measure of how the ion responds to the electric field. This U term is simply everything in this equation except for the electric field. So it simply says how the speed varies as we vary the electric field. Mobility is a microscopic property. So remember we talked about conductivity before. Conductivity looks at the entire solvent. It's a bulk property of the solvent. But the ionic mobility just looks at the individual ions. And we have many different factors which affect the mobility of our solvent. So we looked at ionic size. So we'd think that would affect our ionic radii. If we look at our group 1 ions, lithium is absolutely the smallest ion, but the ionic size isn't the main factor. We need to look at the hydration shells. So we spoke before about how lithium, even though it's the smallest ion, has the largest primary hydration shell. So we have these two factors. We have conductivity, which is a bulk property. We have mobility, which is a microscopic property. So can we link the two together? It would seem logical that we should do this because ultimately the bulk property that we observe, the conductivity, must be a factor of the mobility. And it turns out that, yes, we absolutely can relate these. The derivation of this is outside the scope of this course. However, when we work it through, we find that there's a connection between our limiting molar conductivity that we spoke about in the last few videos and the mobility, this U factor, of our ion. And there's a very simple relationship between them. If we simply sum up the contribution from the positive ions and the negative ions, we can derive the limiting molar conductivity. The next factor we wish to look at is transport numbers. As said before, we have looked extensively at bulk properties in terms of conductivity, but we need to think about what's going on. We need to think about how the charge moves around in our solution. So how do we look at the movement of the individual ions when all we can measure is the external current I? So what we need to do is we need to consider both sides of this particular cell. We need to factor in the external circuit going through the ammeter, and we need to consider the internal circuit going through the solvent, because the total current will be the overall sum of all components. So inside the solution, we have anions carrying our negative charge across. We have our cations carrying the positive charge to the other electrode, and this results in a flow of electrons around the external circuit. The transport number simply represents the share of the total measured current carried by any individual ion. So it's a fraction. So the transport number simply indicates how much of the current is carried by the cation and how much is carried by the anion. Ions rarely carry an equal share of the current. It's tempting to believe that since we have an equal number of positive charges as negative charges, that each would carry an equal share, but it depends on the mobility. If something is more able to move through the solution, if it's able to move more freely through the solution, it can carry its charge faster through the solution and can deposit it quicker at the electrode. So we need to consider this factor as well. It's a tricky thing to visualize, but let's start building up how charge is transported through a solution. If we look at our standard solution, we have our two electrodes here. We're going to do a few things to this system. Firstly, we're going to divide it into sections. So we have an area close to the anode. We call it the anode area. So this is the area space which is mainly affected by the anode. Likewise, we have an area space which is affected by the cathode. And in the middle, we have a bulk area which is not affected by either the anode or the cathode. The next thing we need to say is that the overall charge in each section must be zero. So whenever we have a solution in equilibrium, the charge is moving around, we must have an equal charge distribution. So in the anode area, we have an equal number of positive and negative charges. In the bulk area, we also have an equal quantity of each, and likewise in the cathode area, we have an equal quantity of each. So this sets up our model to start consideration. So let's move into what happens when we allow a current to flow, when we connect those. We're going to say that the cation is twice as mobile as the anion. Okay, that's the first thing we're going to say. If we have a very small, nimble cation but a very big, bulky anion, then we would expect it to move quicker and it would resolve charge imbalance quicker. So let's think about what happens. The cations, they pick up, let's start with these. Cations pick up 3 electrons from the cathode and are removed from solution. So these 3 pick up an electron and are removed from solution. Likewise, to keep the external current equal, the electrons flow through the circuit and redistribute themselves, which means the anions have to deposit 3 electrons at the anode. These are also removed from solution. So what we've ended up with is a charge imbalance. So we need to rectify this charge imbalance in each area. The bulk area is still charge balanced, but the anode area is not, and neither is the cathode area. So it would seem sensible that the rectification of charge comes from the bulk. So how does this happen? Well, we've said that the cations are considerably more mobile than the anions. So let's say they flow twice as fast. So we would expect 2 cations to flow in here to make a 3+, and we would get 1 anion flowing out of this area into the bulk, giving us an overall 0 charge in the cathode area. We would expect the same thing to happen in the anode area, and this gives us an equal distribution of charge in each area. There are several ways of accomplishing this. We can have all 3 charges being balanced by one type of ion, or we can have it going the other way as well. In this example, we have simply said that our anion is less mobile, so only one anion moves for a pair of cations. So what we can say here then is that the cation is carrying twice as much current as the anion. But notice what's happening. We get a depletion of charge happening in the anode area and an accretion of charge eventually in the cathode area. This will become more significant as we go through the course. Experiments such as this allow us to determine ionic transport numbers. If we look at a table of data, it's immediately quite dry to look at, but let's just quickly sort out a few things. This solution normality is simply a way of reflecting the basicity of the ions, and the only thing we need to worry about is it's related to the concentration. If it's related to concentration, it's related to activity. So let's look at what happens as we go down a particular group. So let's look at the barium chloride. What we see here is we have a gradual decreasing in transport number. So that means the barium is carrying less and less of the charge as its concentration increases. That goes along with what we were saying about ionic atmospheres and the solvation shells. So as we increase the number of solvation shells, the more resistance there is to that flow. So barium is less able to carry the charge. So we see that decrease. If we now look across the next 3 columns, looking at the group 1 cations, they follow the mobility we mentioned earlier. Lithium chloride has the biggest solvation shell, so is able to move through less. It experiences more drag, so its mobility is decreased, which means it's less able to carry that charge. If we look at sodium, it's slightly better able, and potassium, it's about 50-50. Okay, so we can see all of these values here are, with the exception of lithium, around about a half for a lot of them. So if we've got a transport number of about a half, that means there's an equal share of current being carried by each of the anions and cations. However, let's turn our attention now to hydrogen chloride, or HCl. In this case, we're seeing a proton transport number which is exceptionally high. So everything else is about a half, plus or minus a little bit, but the proton transport number is huge. It's carrying over 80% of the current. Why is it that protons are able to carry this? And it comes down to the phenomenon known as the Grothuss mechanism. We covered this very briefly in first year, but let's look at it again. Remember, protons appear to be unusually mobile. They are moving much quicker through the solution than we would otherwise predict and carrying a massive share of the current. So let's think about what is happening. We're doing these measurements in water. So what is water? Well, H2O. If we populate our system with more and more water molecules, and then think about what happens as we introduce a hydrogen ion. Well, remember, this is inherently unstable. It will associate with a water molecule to create the hydroxonium ion. This can then undergo a proton exchange with a nearby water molecule, which can then undergo another exchange and another one. And as you can see, the hydroxonium ion appears to be moving through solution, which will then deposit a proton at an electrode. So it's not that an individual proton is particularly mobile. It's just we have this Grothuss exchange. We have this continuous proton transfer throughout the solvent. And that's what's driving our proton transport number. Makes it much higher than we would otherwise expect. Whenever we consider what happens at an electrode, an ion comes in, it drops off its electrons or picks electrons up and forms a neutral species. It then needs to move away from the electrode in order to let other ions at the electrode. This process is diffusion, and we need to think about how diffusion behaves as well to understand our electrode processes. Diffusion is fundamentally a transport across a concentration gradient. So if we have a system where we have a very concentrated analyte at one end and free solution at the other end, this is going to diffuse across that concentration gradient. It's going to distribute itself until we have an even concentration. Diffusion applies to all species, but we need to particularly focus on neutral species for the reason that we said. These things need to diffuse away from the electrode surface. I'm going to call you back to your first year thermodynamic diffusion argument. Go and reference that, go and have a look at that, make sure that you're happy with that content. But what we're going to look at here is we're going to look at a concentration gradient. We're going to look at how the concentration varies over a region of space. So if we have a concentration gradient, if there's a difference in the concentration, we would expect to have diffusion. So at what rate does that particular species flow? So what is its flux? So that's what we're looking for. We're looking at how it flows through a given space. We propose a particular model such as this, where we have the rate of flow, so the flux J, is equal to some constant multiplied by the concentration gradient, so dc by dx, the rate of change of concentration across a given area of space. So if we look at this, we think, okay, well, our concentration's high on the left, low on the right, so that means our concentration gradient is pointing to the left. But if we think about the direction of motion is going to go to the right. So this means we have a negative value here. This is exactly the same as a rate law that you've looked at in kinetics. It's the same mathematics, it's the same expression, so you're comfortable with this. So what would happen over time if we suddenly let this system equilibrate? Well, we're going to get a flow from left to right across this little region of space, and the boundary between it becomes more and more diffuse, until we get to a point where there is no difference between the two, so the rate of change of concentration with distance becomes zero, and we have no more flow happening. This relationship is known as Fick's first law of diffusion, and it simply states that the flux is proportional to the change in concentration over distance. The d term here is the diffusion constant, and we can determine it fairly easily from this particular relation here. There's no need to derive it, but this is known as the Stokes-Einstein relation. Notice that there's no charge present in this equation at all, and that diffusion is purely related to viscosity. So this eta term here. Now we've seen this already today. We've looked at this and we've considered it in terms of ionic drag forces. This kBt you should recognize as the thermal energy in the system, so the thermal energy per molecule in that system. And remember that A is our hydrodynamic radius as well. Chemical potential also plays an important role in diffusion. Concentration is fundamentally linked to chemical potential, which means we can use our chemical potential understanding from previously. This allows us to determine a thermodynamic force for diffusion. So remember that the chemical potential is simply the partial Gibbs energy of a particular component. And we're looking at A, the activity, in this case. So remember, it's a potential, so if we do a derivative of this, this will give us a thermodynamic force as such. So we simply do a first derivative of this with respect to x. So that's across that concentration gradient there. If we're using an ideal solution, we can replace the activity A with our concentration C, and we end up with this expression here. We get a very straightforward diffusion force on our species. One thing I'd like you to consider is, why does the standard chemical potential disappear in the derivative? So we have a great deal going on. We have diffusion and migration processes happening. We have diffusion due to concentration gradients. We have migration due to electric fields, but we need to consider both whenever we're looking at our system. Ions migrate to the electrode. They give up electrons, or they receive electrons, depending on whether they're anions or cations, and become uncharged species. And those uncharged species must diffuse away. So we have three forces going on here. We have the diffusion as things move across their concentration gradient, and we have the electrical force, which is drawing our ions to the electrode. And fundamentally, each of them is experiencing a drag force. But only the electrical charged species are subject to that electrical driving force. Okay, we've covered a lot of concepts. Let's start putting them all together. We see many of the same terms appearing. So in our diffusion, we say that we've got a solvent factor and the thermal factor, but we also have our ionic mobility, which again has a solvent factor, but now we're looking at the charge on our ions. We've got a simple equality here, and we can rearrange these and substitute values in to express our ionic mobility in terms of diffusion. So this allows us to relate them via the Einstein relation. So for a given molecule, we can relate our diffusion coefficient to the charges. But if we want to look at it in terms of molar terms, we can relate it to our molar thermal energy and the Faraday constant. Okay, so that gives us our ionic mobility in terms of the diffusion constant. This can also be related to molar conductivity. So remember what we did last time looking at molar conductivity, and we have a link between our mobility and conductivity from the start of this session. And this allows us just to simply do a quick substitution to express our molar conductivity in terms of the diffusion coefficient. In summary, we need to look at ionic mobility. Ionic mobility is key to how ions move through solution. If they are less mobile, they have a lower contribution to the ionic current and fundamentally the conductivity as well. Ions rarely carry an equal share. So generally they are carrying an unequal share of that current, with more mobile ions carrying more of the current through that solution. And remember as well that diffusion and migration are complementary processes. They are intrinsically linked, and we have to consider both in our electrochemical processes.